Hello. I designed this course for programmers who have written in Java, C#, JavaScript, or any other C-derived language that uses garbage collection. From time to time, I'll draw comparisons to code written in those languages to the equivalent or near equivalent C++ code. But at no time should you infer that I'm saying that one of those is superior to any of the others. All of these languages, even the much maligned JavaScript, can be used to great effect in professional programming and require a respectable amount of skill to get the job done correctly. C++ is a very powerful language. Its creator, Bjarne Stroustrup, whose name I have almost undoubtedly just mangled, once suggested that C makes it easy to shoot yourself in the foot, and that C++ makes it harder, but when you do, you blow your whole leg off. The biggest complaint about C++ is that it leaks, and that it doesn't protect you from the consequences of your mistakes, no matter how trivial. And that latter statement is true. And as we'll see, the former statement isn't really true at all. C and C++ allow you to write extremely fast and efficient code, but you have to be careful. In some cases, you have to be very careful. During this course, I'm not going to try to get you from 0 to 70 miles an hour, or 113 kilometers an hour if you like, but I will get you up to a respectable and sustainable highway speed. By the end of the course, you should be able to write working C++ code absent of any glaring mistakes in memory management. Let's start by looking at how things go wrong. If you've been programming in C++ for a while, this won't be much of a revelation, but if you're new to this, you may hear some things that surprise you. Believe it or not, the heap is not your friend. You'll find this especially true if you're writing multi-threaded software and aren't using thread local storage. Since all threads in your application share the same process heap, allocating and deallocating memory locks the process heap until those operations complete. It's as if all the threads synchronize versus heap activity, and that slows down your software, even if you don't have to share information between threads. Your application loses some of the efficiency of parallel, or at least multi-threaded, processing. You might not have to use the heap at all, however. If you can keep data structures small, only work on small amounts of data at a time, and allocate on the stack as much as possible, you can avoid the pitfalls that come with using the heap. The upside of having megabytes or gigabytes of memory available to your application is that you can write a lot of very fast code that can keep its working data in memory just about all the time. The downside is that you can start to get sloppy, particularly when allocating off the heap for small items. For example, in my industry, a common piece of data is a city or station code. It's the way the airlines designate airports. Orlando International is MCO. Los Angeles is LAX. Almost everybody knows that one. The station codes are 3 characters long, and they're going to stay 3 characters long for a very long time. This means that one can easily store them in a 4-character buffer, or an 8-character buffer like this one just to be safe. Nevertheless, I look into source code just about every day and find something like this. Since that string class instance has to copy the constructor argument, and it allocates off the heap to do so, that's either 4 or 8 characters of data carved off the heap into a little chunk. The heap management code expends its own memory, creating a block to track that little chunk, and all the other little chunks it's already allocated. When you finish using that station code string, the chunk goes back into the free list. What starts as a monolithic block of memory gradually turns into a checkerboard of smaller and smaller blocks. Breaking the heap down into little chunks of memory like this is called fragmentation. It also happens in garbage-collected languages. Most heap management libraries will not attempt to merge one small chunk with another small chunk in order to make a less small chunk just because you handed the memory back. The libraries just keep the chunks around on the chance that another request will come in for a chunk that size. Let's think about what happens if you allocate a lot of little chunks and then have need of a very large chunk. After a lot of fragmentation, the heap manager may find that it can't satisfy the request without consolidating a lot of the smaller chunks it's holding as free. So it sets about the task of merging chunks and rewriting its lists, and nothing gets done until the heap manager finishes that task. Sometimes that can take longer than you'd like, and sometimes it can bring down an entire server. I admit that pulling down an entire server that way is an extreme case, but I've seen it happen. Another way programmers get sloppy is inside loops. If the code between the new and the delete is long enough, or something happens in a later release to cause a premature loop exit, this code leaks memory. If you have to instance inside a loop, and you should avoid that, this rewrite at least won't leak. If you're not taking the higher order function path, as illustrated here, this is at least better than this. Here's something we all do, and the newer it is to us, the more we want to do it. Use the latest thing. I agree that there's something just amazingly cool about writing this line of code. It's certainly cool compared to doing it the old school way. Here's something to remember. If you're not going to do magic string things with the data in the buffer, don't use a string to store it. You're creating extra work for the program to do for no obvious benefit to anything other than your ego or sense of being modern. It might not be obvious these days, but we did manage to write some fairly complex and long-lived code without having these conveniences around. I'm not complaining. I like the new shiny stuff as much as anybody, but it isn't always the best way to do the job. I'll review these ideas and a few more later in the class. Now that we've skinned the surface of what can go wrong, let's go in depth, starting in the next lesson. Let's talk about staying in your own sandbox. Because C++ doesn't have built-in range checking on arrays and strings, it's possible to walk right off the end of a memory range or off the front of it. If you know of the standard template library vector and string classes, you're thinking that they have built-in range checking, which they do and they don't. The index operators don't have it. The at methods do, so you'll need to use the at method if you want the built-in range checking. STL aside, in older code or non-STL code, you'll need to do some range checking. If you're thinking that means a performance compromise, you could be right, but I think that safety is almost always better than speed in these situations. Crashing is the ultimate slowdown, right? So here's an example of a last index function that sort of shows you both ends of the problem. I have to go to the end of this range and search in it. I have to not walk off the front. So we start by setting it up at the end of the range, which is always the length -1. Start at that point because it's last index of, right? Walking backward, making sure never to get past the beginning. My test pointer always has to be greater than or equal to the beginning. And return when I find it, and then return -1 when I don't, because -1 is the only unacceptable return value for an index since we know we can't go past the beginning. You're not going to have an array of 4 billion things to search. Nobody ever does. So -1 is a good choice. The range checking here is explicit, but it's not slow because it only occurs during initialization. We don't have to test the range of the pointer during each iteration because it's bounded and can only fall within the range of data we've been asked to test. Another way to look for errors is to abstract your memory management through functions that allow inspecting the memory for overruns and underruns once they've been used. Some debug runtimes do this already, but it's a good idea to know what it looks like. Let's look at an example of a library that allocates character buffers and can perform limited testing on boundaries. It's written to disappear in a release build so there's no performance impact. And it's a straightforward idea. When the caller requests a block of size n, the library allocates a larger block that looks like the following. The control block holds the requested memory size and a Sentinel block, stored before the actual buffer. The allocation function adds a Sentinel block at the end as well. This is how it can, in a limited fashion at least, detect both overrun and underrun of the allocated block. With a Sentinel block size of 8 and a requested block size of 16, here's how the memory would look. Those first 4 bytes are just the size, followed by the Sentinel range, lovely allocated block, which I'm going to initialize to zeros because that's how I like to do things, followed by another Sentinel block. Let's take a tour of the code itself. The first thing is the definition of the Sentinel block, which I've called oversize. The next is the definition of the Sentinel itself, which should just be any character that you don't expect to find in a long run. It could all be zeros. It shouldn't be the letter X or space or something like that, because that might be actual data. During the allocation, it follows just as I said before. Create a block large enough to hold the control block at the beginning, the extra sentinels at the end, and of course the memory they asked for. Fill in all the parts as is appropriate. Sentinels in the Sentinel block, the size where it needs to be. Capture any exception thrown, because in this case, I'm choosing to return null for a failure to allocate rather than throw an exception. You could do that any way you want to. The important part in this is that before the pointer goes back to the caller, it gets incremented by the size of the header. We don't want to return the header. We want to return working memory back, not the data that we're interested in for tracking whether or not there's been an overrun or an underrun. At the far end, and I'm skipping over the failure test, when we deallocate, it's just a matter of taking back the pointer that we handed out in the first place, taking off the size of the header, and then just deleting that buffer. Cleanup is pretty tidy. When the coder wants to test the integrity of the memory she just used, she calls buffer bounds fail with that returned memory pointer. The first thing it does is map a memory header over the start of the block allocated by buffer allocate. We don't know right away if we can trust the size field of the header because there might have been an underrun in the code using the block. So the first test we'll perform is checking the Sentinel block in the header from back to front. We'll walk back from the first part of the memory returned by the coder because that's the first place an underrun can occur in most circumstances. If we can walk back through the entire Sentinel block without finding a disturbance, we can probably trust the size field in the header. I say probably because this scheme depends on you knowing your code well enough to size the Sentinel blocks. If you never iterate backwards through a block, the Sentinel testing might not be critical on the front end, which also presumes there isn't any unusual pointer math that might go bad because of a sign bit flip when using signed offsets. If you assign 20,000 to a signed short integer, the result is negative. I've seen legacy code that did this quite unintentionally while determining memory offsets, and the result was a ruined index. At the time it was written, no one ever thought the index might grow beyond 16 kilobytes, and in practice it almost never happened. But once it did, and that was bad. So, once we think the control block is more or less intact, it's time to move to the Sentinels at the end of the block. Testing starts at the returned pointer plus the size offset, and moves forward to the end of the block. If the block contains nothing but Sentinel values, nothing, at least that we can track, has gone wrong. Note that this technique doesn't work when you have a defect that adds a value like 100,000 to a pointer, but when you walk a pointer sequentially along a contiguous buffer, this will capture virtually all the cases. You may find it useful to write a version that doesn't use symmetrical buffers when you know the code in question works in one direction only backwards, only forwards. Maybe you don't need Sentinels at both ends. When you can't use the STL iterators and algorithms to make sure that you stay in your sandbox, this is the sort of code you can use to track boundary issues during testing. Time for a discussion of something that is near and dear to the hearts of all C++ programmers, memory leaks. One of the most common criticisms of C and C++ is that programs written in them leak memory. Programs can leak, to be certain, but those leaks had to be written. Someone sat down and wrote leaky code. That's the cause of memory leaks. Bjarne Stroustrup, the inventor of C++, summed up the solution to memory leaks thusly: don't write any. What seems to be the easiest way to avoid memory leaks is the most insidious. It's called the sandwich pattern. In C, it's a malloc followed by working code, followed by a free. In C++, it's a new followed by working code, followed by a delete. Neither usage provides any reasonable guarantee that later maintenance coding won't somehow cause the free or delete to be skipped. More to the point, there's no guarantee that an exception thrown locally but handled farther up the call chain won't cause a memory leak. Don't use the sandwich pattern. Use auto pointer, shared pointer, or unique pointer. These will guarantee, as much as possible, that memory is cleaned up even in future code releases. This depends on your writing proper destructors in your classes, of course. Remember, you're the one that writes memory leaks, not the compiler. Speaking of destructors, here's a way to leak that sneaks up on you. Forgetting to maintain the virtual destructor chain. At object destruction time, the generated code works its way back up the derivation chain, but stops at the first non-virtual destructor. That can abandon memory and resources allocated by parent classes all the way up to the base class. Here we see a derivation chain where CO5 derives from CO3 by way of CO4. The CO3 class declares a virtual destructor, as does CO5, but the coder of CO4 in the middle forgot the virtual keyword. Any memory allocated by CO3 will be leaked during destruction. Of course, we can fix this by adding the virtual keyword. This can be difficult to track down because coders will look at the individual destructors in the CPP file and assure themselves that all the memory has been released, but forget to look in the header file to make sure that the keyword virtual didn't get dropped along the way. Next, let's talk about function calls and method calls with objects. Don't pass objects through call interfaces, particularly just to access one feature of the class. If you need to pass an entire object through a call interface, either pass a reference or a pointer, whichever makes you more comfortable. Passing instances through a call interface causes the compiler to generate a copy because the default in C++ is passed by value, not by reference. Passing by value means making a copy so that the original object can't be modified. You can always use const to ensure that the by reference instance can't be modified by the code that you're calling. I know this doesn't seem to be about memory leaks, but think about it. If the class you pass happens to leak memory, that leakage will be aggravated by passing a copy of the class through a call interface. Even if the class doesn't leak memory, creating read-only ad hoc instances can fragment the heap, something you try to avoid. If you have to allocate off the heap, use the standard template library wrappers to manage class instances. These class templates will ensure that everything gets cleaned up even in the face of premature function exits and exceptions. They handle copy and move semantics as well. You'll start writing code as if you're using C# or Java or another garbage collected language. Getting into the habit will let you think about the task at hand rather than worrying about memory leaks. The first example here shows sort of the sandwich pattern. I'm going to create a new instance, and at the end I have to delete the instance, and what happens in the middle could go terribly wrong, and I'm pretty sure it'll leak. Here, by using auto pointer, I guarantee that no matter what happens, except ultimate catastrophe, this instance will get cleaned up. There's another way to instance classes that isn't used nearly enough: automatic instances. When you use an automatic instance on the stack, rather than an instance off the heap, the compiler will generate code to run the destructor and release the memory just like it would for plain old integers, floats, and character arrays. The only time to avoid this is if your class has a large memory footprint. Say, an internal character array of 32 kilobytes that doesn't come from the heap. You shouldn't do this unless you can be sure that there will never be enough instances to eat the available stack memory. Classes with large internal memory requirements should be rare in practice. Even 1 kilobyte of memory per instance isn't deadly. If you're a fan of the factory pattern in C# and Java, you'll be pleased to find that it works well in C++. But the question of lifetime management is a bit trickier. If you're working with a third-party library, you'll need to know how the factory methods expect lifetime management to be handled. Will they clean up after themselves, or will you? There are 3 methods of approach. You receive a pointer to an object and delete it when you're done. The factory exports a method you can call to return the instance for cleanup, and the factory returns an auto pointer-based instance that cleans itself when it goes out of scope. Let's look at an example of how an application gets into trouble. Here are some small representative classes for a hotel check-in application. A reservation contains guests and rooms and can return pointers to guest instances and room instances. The reservation class manages those lifetimes so that users of the class won't have to. There's a function call, perhaps part of a factory class, that returns a reservation when supplied with a reservation ID, but the factory doesn't manage the lifetime of the reservation instance. That means accessing a room or guest has different semantics than accessing a reservation. And maintenance coders will tend to assume if they don't have to manage the lifetime of the room and guest instances, they don't have to manage the lifetime of the reservation itself. In the first case, there's nothing to keep you from using auto pointer against the returned pointer to ensure deletion. There's another tack you can take when dealing with legacy code or library code with dubious lifetime management. One rather long-lived library I use has a text buffer class that accumulates large buffers quite nicely, but has the unfortunate habit of handing back a malloc pointer when asked to provide an ASCII Z-string copy of that buffer. This was reasonable back in the days when our code was more C-like, but today anyone receiving a string buffer expects to be able to use delete, not free. Write a wrapper class that accepts a pointer to the class with the unfortunate memory management and capture what it returns in that class. When the code invokes your wrapper's destructor, clean up the pointer to the captured data in the manner appropriate to the class. Don't forget that there are two kinds of delete in C++, object delete and array delete. A compiler may not flag an inappropriate use of delete when array delete is more correct, but if the array happens to contain objects, their destructors won't be called with object delete, and that can lead to memory leaks. This wraps up our look at many ways that memory leaks can occur and how to avoid them as much as humanly possible. Remember to augment these ideas with regular code reviews, especially when you receive updates from coders unfamiliar with your codebase, and to make sure to document the memory management requirements of your classes and functions in an easy-to-understand way. You want to make working with your code as easy for newcomers as it is for veteran coders. I'm calling this section You Can't Go Home Again, although I might well have just said that with pointers, there aren't any do-overs. A serious mistake one finds a lot in more complex C++ code is the inadvertent reuse of a deleted pointer. This almost never gets written into the original code, but maintenance coders can introduce it. It usually looks like this. The code starts out with every good intent to satisfy a condition and delete a variable, and then probably should have returned right there, but for some reason continued onward. Then about 20 lines later, or 30 or 40 or 50 lines later, somebody with every good intention in the world reuses the pointer. The most common causes of this mistake are functions or methods that are too long or too complex. Maintenance coders on a tight deadline sometimes don't look too far away from the site of the defect they've been tasked to fix, and will miss crucial clues that they've just introduced a defect. This can also slip through build phases if the warning level of the compiler isn't set high enough, or if the compiler doesn't check at all. The problem is that the now deleted pointer could still point to useful memory, and may even have the same value that was there when it was deleted. And this depends on what's in memory at the time, whether you're running the code in debug or release mode, and whether or not your test cases hit all the relevant code in the module. In multi-threaded applications, unit testing of the logic flow may or may not be able to produce enough threads to cause heap changes during the tests. In single-threaded code, this might well work as if nothing had gone wrong, at least until it ends up in a customer's hands. In multi-threaded applications, this error usually shows itself at least by the time the quality assurance team gets to it, but it may be hard to diagnose because the symptoms may be different each time it's reported. Sometimes it will result in an exception, which might or might not be caught, depending on how much exception handling surrounds it, or it may result in an unusual code branching choice later on, a choice taken that doesn't seem to be in accordance with the data present, or what you think was the data present. Unusual values will show up in logs or databases or be presented to users, all because the memory referenced by the pointer was still usable, but contained different values than were present prior to the delete operation. To those more familiar with C# or Java, I'll point out that the delete operator simply severs the relationship between the pointer and the memory to which it pointed. Unless the code takes the time to erase the memory itself prior to the delete, nothing much happens until the heap manager decides to reclaim or reuse the block. The best way to defeat this mistake is through static analysis tools like a C++ lint. If you've not heard of lint, it's a program used to read C and C++ source code to look for suspicious coding practices that can be detected by static analysis. The name comes from a term for bits of fluff and fiber found in sheep's wool, although you and I are more likely to think of that material clogging the clothes dryer filter. If you don't have static analysis tools available, there is a way to make this mistake more likely to reveal itself during unit testing. Set the deleted pointer back to null in any non-terminal portion of the code. That is, if you're not at the end of the function or about to execute a return statement. So let's do that right up here. Now any attempted dereference of that pointer will cause an exception. So if your testing hits that code path later on, you can't miss the exception. And it's your job to make sure that unit testing hits all the code paths, right? If you want to use static analysis tools, there are several choices available to you, both as open source and paid products. Gimple Software produces PCLint and FlexiLint. SourceForge has CPP Check, the page for which I'm showing here. The CPP Check page points out that you shouldn't rely on only one method of checking your code. Static analysis, instrumenting with tools like Valgrind, and extensive testing are all required in order to do a thorough job of testing your application or library. The relationship you have with your code, the libraries and compilers you use, and the data you receive and manage is not a trust relationship. Something I see as I move from one compiler to another is the variation in what the compiler will tell you about your code while it's being built. Back in 2005, a certain compiler might warn you about uninitialized variables if you set the warning level high enough. The 2012 release of that compiler now properly tells you that the uninitialized variable is there and treats the situation as an error, not a warning. That's a vast improvement, but it's not a cure. The problem is that your code, and in fact your entire application or library, doesn't live in a vacuum. It might be ported to Linux or to Windows, depending on the platform on which you first wrote it. It might not always be built using the compiler you expect to be used. So, initialize everything. In some older development environments, the compiler provided safe values to uninitialized variables, masking that you hadn't supplied a value yourself. If you had code like what you're seeing here, where you test a pointer for null, if it is null, you initialize it, and then you go about working, this would always work in a debug build and fail in a release build because the pointer would simply contain whatever was on the stack or in the data segment or wherever it happened to reside. The debug build would put null into that pointer. This applies to not just pointers and buffers, but to integral values used as offsets or indexes, and booleans used as branching gates. So, set pointers to null, integers, and characters to something reasonable in your context, and booleans as appropriate to their purposes. And remember, in C++ it's safe to delete a null pointer, so even if you never allocate memory using a particular pointer variable, it's always safe to delete at the end of the scope, or in the destructor. If you came up through classic C, you know that calling free versus an uninitialized pointer was a bad idea. C++ cleans this up with delete, but the old malloc behavior is still there. Of course, you're not using malloc anymore, right? So what can you do to make sure that things don't go awry? Never assume that an allocation will work. Either use exception handling or test for a null result or whatever works in the environment. If an allocation fails, you can't assume that you'll have enough resources to try again. After all, you don't know if you asked for too much memory or too large a chunk or whether some other action has corrupted the heap. The best you can do is strive to tidy up all your resource allocations and get out gracefully. It's good practice to log the event and exit, but you can't plan on being able to allocate memory for a working buffer. One approach to this issue is to simply create a 1 or 2K static buffer in the data segment as a global variable. Don't wince at that, it's a legitimate use, and use that buffer to write out a post-mortem of the exception before exiting the process. Don't assume that the arguments to your function will always contain valid data, particularly when the caller passes a pointer. String pointers might be null or point to empty strings. Integers might have out-of-range values, for example, negative array offsets caused by incorrect mathematics on the part of the caller. If you're writing a web application, never trust your inputs. Far too many exploits of web applications, document presentation software, and script engines involve deliberate attempts to overrun buffers in order to execute arbitrary byte sequences as code. If you have to use fixed-length buffers in some part of your code, length test the incoming data and either truncate it or reject it. If possible, exchange the fixed-length buffers for something more adaptable and safe. Use safe versions of functions whenever possible. If your compiler has safe string and memory libraries, use them whenever you can. Microsoft has a set of safe string and memory functions designed to prevent overruns, and you can find out about them at the link that you see here. Now I'd like to look at a classic mistake I've seen a lot. This mistake gets made time and again, usually by maintenance coders coming in later to work on code, and we call it an accidental use before test. It looks like the code that you see here. The original code almost always forgot to check to ensure that the object was allocated properly, and someone came in afterward to put in the safety check. This example is pretty obvious, but in a function with a lot of data values, sometimes the dereference of that allocated pointer will be lost in the crush of declarations and initializations. Here's a proper rewrite of that for compilers that are returning a null result into a pointer if the allocation fails, using an auto pointer here to make sure that the cleanup always gets done no matter how we exit the function. This one's pretty safe, and we don't make the mistake of trying to access data that we're not sure we got. Here's the same function again, this time capturing an exception thrown when the allocation failed. I know that the trust nothing attitude seems paranoid, but a guarded approach to allocations and incoming data is what works in a world where hackers are trying to get in through any door, window, or cat flap they can find. It's absolutely correct to set up interface contracts with those who call your code, and equally correct to doubt that your callers aren't following that contract. We've just spent some time reviewing defensive programming techniques. Academics advise using defensive programming, and some professionals respond that using it hides defects. Furthermore, defensive programming can and will slow down your application to some extent. Both of these assertions are true, and yet I still recommend defensive techniques. Why? Well, after a quarter century of programming, I've come to the conclusion that defensive programming is worth the effort. Applications that don't check every detail of their environments may be vulnerable to hacking. There are very few exploits designed to make your software determine the wrong amount of sales tax. They want to inject code or steal sensitive customer data instead. They don't do that by trying to force you down an incorrect logic path. They do that by gaining access to memory through unchecked buffers. If nothing else, the attacker might be able to create a denial of service attack by consistently crashing your application. Your customer or your customer base doesn't want an application that crashes. The execution speed of a crashed program is 0. Application crashes risk data loss or corruption. Your defensive code should be writing defective inputs and exceptions into your debugging logs, and you should be reading those logs. Your unit and system testing should exercise all code paths, and you should have specific test cases with edge and corner case data inputs. Your quality team shouldn't be afraid to write test-to-destruction cases into their plans. The old joke says that there's nothing wrong with being paranoid if they really are out to get you. The history of software in the 21st century so far shows that, like it or not, there are groups and individuals out there ready to do harm by exploiting weaknesses in the software that we write. There are very few of us that haven't spent some time cleaning malware or extortionware off a relative's computer, and few of us that thought it was an afternoon well spent. By writing smarter, more defensive code, we can keep our customers and ourselves from losing data due to crashes. We can keep enterprise-critical systems running for longer intervals. We can lower the risk of exploits. Defensive programming may not be pretty, but it works. In this lesson, I'm going to discuss memory assets shared between threads and managing data that has to flow between them. A lot of programmers shy away from multi-threading in software because of the problems that arise when multiple threads all contend for the same resource. Sometimes the issues arise because of the complexity of the algorithms involved in solving a particular problem, but we needn't look at those advanced cases to see the problems. We can look at something closer to home, configuration data. I've worked on a number of highly configurable applications over the years, and configuration management on a large scale is always a problem. Let's start with read-only assets. The easiest scenario to manage revolves around static read-only data that can be loaded at initialization and simply handed out on demand throughout the runtime. One needn't worry about simultaneous access from multiple threads because even if a particular read or copy operation isn't atomic, the value being read doesn't change, so there's no harm. Now, if your customer can suddenly decide not to apply business rule number 51 in the middle of this afternoon, as opposed to every Wednesday or every even-numbered Tuesday, because you can code for that, then you have to think about how to obtain that data. Synchronizing access to that data doesn't have to be the answer. You might choose to issue a query to an SQL database or to a configuration web service each time the question arises as to whether or not to apply business rule number 51. That removes the issue of data synchronization to someplace outside of your code, and there's nothing wrong with that. Whether or not calling outside your application meets the performance goals of the system is something you'll have to determine on a case-by-case basis. At this point, we might revisit the reason for managing access to data in the first place. In multi-threaded applications, especially those providing web services, most operations aren't atomic. That is, they don't necessarily complete without being interrupted by another thread of application code. Assignment operators for classes make copying class objects look like copying integers, but that's a convenience for the coder. Under the hood, we know it's a lot more complex than that. A multitasking, multi-threaded operating system interrupts operations as it deems necessary, opening the possibility that shared data might be written to and read from at the same time. A data reader might have copied half of an object's fields, been interrupted by a data writer updating those same fields, only to resume the copy operation and end up with a corrupted object full of mismatched data. That, at the very least, implies some sort of logic error might be made. At the worst, it leads to exceptions and application crashes. So, in general, we don't allow simultaneous reading and writing of common data, and we just don't allow simultaneous writing of common data. One might allow simultaneous read-write operations where there is no data overlap, but something of that level is beyond the scope of this lesson and this course. Coming back to managing configuration data particularly, you'll remember that I mentioned reading from a SQL database or querying a web service as possible choices for acquiring data without synchronizing access. You might also simply read from a local memory cache as well, and code requiring this data shouldn't need to know how the rest of the application acquires the data. This is a good place to write an abstract configuration interface, either as a library or class, so that you're free to change what happens behind the scenes as the application evolves through time and changes in requirements. This is also a good place for me to mention that the abstracted interface always hands back copies of data, not the actual data. Handing over the address of a string or character array or pointer to a data object is asking for someone to make a mistake and modify the data. Pass back copies. If someone 2 releases from now accidentally tries to write to the configuration data, it won't corrupt the original data cache. Now let's talk about writable assets. You can't all get in there at once. Assuming that the design you have absolutely requires synchronized read-write data access, you have 2 options: critical sections and mutexing. I've separated the 2 terms because Linux developers will use mutexes only. Windows developers have a specific critical section API that they can use in addition to mutexing. You could go low-level here to semaphores and other lock types, but there's no need. Modern operating systems take care of that for you. You just need to use the capabilities they already provide. I've included an example mutex class in the code that accompanies this course that you can use to educate yourself on the general principles. Like most educational examples, it's not production-ready code, so I'm not making any warranties or guarantees that it will work for your particular needs. You should learn from it and write something that works in your application. I'll let you look at the low-level mutexing code whenever you're ready. What I'm going to look at now is how you make mutexing automatic inside the classes in your application that require synchronized access. There are 2 ways to do this. Either write a helper class or derive from a class that provides the infrastructure and locking methods itself. Before we go further, I have to pause to talk about C++ synchronization for programmers who haven't had much experience with it. Using synchronized code always runs the risk of a deadlock situation. That is, too many callers try to access an asset at the same time and keep bouncing off the lock. Sometimes you can bring the application to a halt like that, and sometimes you can bring an entire computer to a halt. This is an area where you want and need to be careful. Let's look at the first way to implement synchronization, seen here as cmutex helper. This class requires that you use your own mutex class instance, probably like the one that's accompanying this course, and pass it either via the constructor or in a method called use. I've added a try method that you can activate with a precompiled definition for purposes of illustration, and I'll get to that in a moment. You can hand a mutex in through a constructor, or you can simply create one using the default constructor and follow it with use. I like to use the try method for a reason that I'll explain later, because it makes your code more flexible. I'm also not necessarily a fan of using the constructor that takes a mutex, because if you fail to get the mutex, you may stay locked. Staying locked is bad. An alternative is to have the constructor throw, which means you have to play a little bit with the code that you write. When you scroll down and look at the lock method, you see why I included try. The precompile symbol try only allows us to write code that throws if it cannot get the lock. Sometimes you don't want to handle things by using exceptions, which is why, in general, asking via the try method is the more flexible way to do things and makes it easier to write your code. So overall, the job of CMutex helper is a bit like the STL pointer wrappers to alleviate the need to release synchronization locks when you leave the scope of an enclosing function. It keeps you from forgetting to do it, and that's the greatest danger when working with synchronized code. You can, with the best of intent not to do so, end up locking yourself out by accident. Here are two example synchronized methods. These are more or less safe when called individually, but you should be able to see that they cannot, under any circumstances, call each other. The second method in the call chain, whichever one it is, will try to acquire the lock when the calling method already has it. While you could decide to make the mutex class itself smart enough to allow access from stacked callers, it just adds a layer of complexity to an already complex situation, which is that you're multi-threaded in the first place. When I've been in this situation, I usually write public and private methods for performing these tasks. The public methods, those used by callers outside the class, always use the synchronized interfaces. The private methods assume that the synchronization locks are already in place and just do the work. The public methods call the private methods. Here I've rewritten the synchronized method of the class to call private work method, which does all the actual work that the outside public interface used to do, but now it does it privately. Anybody inside the class should be calling this after having set up synchronization. Nobody outside can call it so that you can guarantee that the data integrity is maintained. The second approach, deriving from a class that manages the synchronization, I'll illustrate with CMutex user right here. In this approach, you derive your synchronized class from a base class which implements mutex or critical section code, and use base class methods to lock and unlock the assets. When you use this approach, you'll have to remember to explicitly unlock the asset before your synchronized method completes. There is no way for the base class to detect that your method has gone out of scope, so the lock won't be released until the entire instance goes out of scope. That might be acceptable behavior depending on how much work you have the synchronized class doing. It's almost always a better practice to release the lock as soon as you've performed a task or a set of related tasks so that other threads requiring that access can get service. Here is exactly what I'm talking about. Called try, we got in, we did the work. Now we should be releasing, unless you want to wait for it to happen when the entire class goes out of scope. Usually it's bad practice to do that. You might have noticed that I haven't mentioned the C++ atomic keyword at all. As of C++ 11, it's still not entirely worked out, a little bit controversial, and in my estimation, it's better to wait to see how the situation solidifies before going into it further. This should be enough to get you started on synchronizing data in C++ to avoid memory corruption. It's a topic full of gotchas and potential pitfalls, and you shouldn't start writing code without thinking about how to design that part of the application first. This area is one of those where you need to think a lot about how to manage data, who needs it, and how to write class interfaces of sufficient granularity to make getting it right as easy as possible. If you think that this is a bit of a dark art, you're right. With enough planning and attention to detail, not to mention some time spent looking up the topic on the World Wide Web, you will be able to do it, and well. In this lesson, I'm going to look at some of the things that coders try that lead them into trouble. I call them stupid code tricks. Usually one doesn't see this from high-end programmers, and I stress usually. Instead, one finds this coming from middle-of-the-road programmers who know just enough to get into trouble by trying to be clever. clever is almost always a bad idea. I'll speak more about that a little later on. Suppose you were given the following code snippet right here. What is the value of I at the end of the loop? You probably said 21. In fact, it might be 21, and maybe it won't be. The C++ specification, and the C specification before it, doesn't indicate what the value should be. It spends all of its time describing how the for loop should execute, but not on what the end value of the loop indexing variable might be. That's undefined behavior. In software, undefined behavior is a pretty bad thing. It might be that every compiler you will ever use will come up with the same ending value for the loop index, but you still shouldn't modify it yourself, or expect it to have a particular end value. When the specification leaves something undefined, there's no contract. You can't depend on the next version doing things the same way. Why am I bringing this up? There's a class of software defects known as off-by-one errors, or for Star Wars fans, Obi-Wan errors, in which a loop index or other calculated value, a memory pointer for example, ends up off by 1 and never in a safe direction. The two most common causes are incorrect pointer arithmetic and code that tries to be clever with loop index variables. I've seen people write this code before, and it's just not a good idea. In a loop, either you need to be in control or the compiler needs to be in control, not the two of you together. In order to defeat potential memory problems with out-of-range array indexing, I have to recommend not playing with the index variable used by the loop. If you need to manage the index yourself, use while or do while. Another way to avoid out-of-range access and indexing errors is to use vectors with STL iterators in the for-each function. I've illustrated that here. Some people grouse about the call overhead involved in executing this, but if you're writing 20 or 30 lines of code inside a loop, you ought to think about refactoring the loop body out into a function call anyway. Code that starts that way almost always ends badly, several years and several maintenance coders down the road, with the interior of the loop running 50, 60, or 100 lines. It's a maintenance nightmare. Whenever you can avoid it, don't instance classes inside a loop. Many times I've seen code that looks like this. An instance of service provider will handle many calls to provide service without being reinstanced, and yet the coder decided that a separate instance was required each time. That can be unkind to the heap and definitely affects performance. I saw an extreme case of this once where the coder opened and read a configuration table from a file repeatedly in the loop, instead of caching it at startup time. Not only was that bad memory management, it was just plain bad coding. For this situation, what you see here is the faster and cleaner way to handle the coding. Take service performer outside, one call to the constructor, and as many uses as you need. One of the biggest weaknesses of C++ is the need for header files that tell the compiler how to generate function calls and lay out memory. Header files aren't intrinsically bad, but they lead less experienced coders to think they might be able to access data that isn't theirs by doing a little pointer math, particularly on parts of the class that you've declared to be private. I know you won't do it, and I won't do it, but somewhere along the way someone might try it and you'll end up debugging that code. The trick can even work for a while, but it falls apart with classes that use multiple inheritance, which itself is already a big pile of trouble. You won't really know where data is stored down the inheritance chain either, and that won't keep people from trying to get to it. The location of data members also depends on the default byte packing configuration of the compiler, so by now you can see how rocky this cart path is becoming. Remind the team to play by the rules, and keep in mind that good code review practices will usually find this and take it out. The takeaway lesson here is that if you're trying to be clever, don't. If you look at a piece of code and congratulate yourself on how clever or tricky it is, rather than how correct it is, then do it over. There's a principle involved that isn't very subtle or very politically correct or even polite, and it says just this: don't be stupid. It might take you a while to realize it, but being clever is just being stupid. Some languages might shield you from the consequences of too clever code or even disallow compiling it. C++ as a rule will let you compile just about any clever trick you can write, but you'll pay for it down the road in defect reports, missed deadlines on releases, and weekends of overtime spent in the debugger. The very old joke punchline to the question, "How do I get to Carnegie Hall?" is practice, practice, practice. Programmers don't have a concert hall for performance aspirations, but we do have careers, and the answer to the analogous question is best practice, best practice, best practice. Not all of what you're about to see applies strictly to memory management, but following these guidelines will lead to better code with fewer leaks and overruns. If data doesn't have to come from the heap, don't take it from the heap. Unless the function you're writing is recursive, or you're in an embedded environment, or the class in question has large automatic allocations of memory, most of the time you don't need to bother the heap in order to instance a class. If you know you're in an environment with severe stack restrictions, then do what's right for that environment. Take data off the heap. Think about what needs to be done and then do the right thing. When data or classes have to come from the heap, use the STL pointer wrapper classes to ensure that everything is cleaned up. You can enjoy the same sense of freedom that garbage-collected language programmers experience by simply making it impossible not to clean up after yourself. If and when possible, use makeshared from C++11 and makeunique from C++14 to generate pointers. The new specification discourages the use of raw new in your code except at the lowest levels. Manage data access through abstract interfaces. The less callers know about what's behind the interface, the less they'll be tempted to exploit it. Loose coupling through well-defined abstract interfaces is one of the strongest ways to foster reuse and limit tuning of outside code to take advantage of perceived features in your implementation. It's also a strong tactic for future-proofing because you can change what happens behind the interface without requiring changes to outside code. Write boring code. Dr. Michael Covington of the University of Georgia, Athens, suggests in a blog post that a lot of good programming relies on knowing what you're doing, not just knowing a lot of different buzzwords or techniques. He goes on to say that when he looks at the code written by those we acknowledge as great programmers, Niklaus Wirth, Brian Kernighan, and Andrew Heidelberg being examples, that their code is simple. It almost looks like code one finds in beginner texts on programming. It's intended to solve the problem at hand, not employ a specific technique or exercise a modern and popular design pattern. I sum this up by saying, write boring code. Boring code is plain, easy to read, and easy to modify, within reasonable bounds anyway. It comes in small chunks of functionality and doesn't require detective work to determine how those chunks work together. It doesn't make assumptions about the data it receives or the responses it returns. Boring code even annotates itself, and has enough inline commentary to enable later coders to determine the intent and outcome of calls to the class, methods, and functions. Make your solution fit the problem, not the other way around. Don't try to pigeonhole problems to fit the solutions you've memorized. While it might be possible to break down a geometry proof into algebra so that you can use the quadratic equation, that's not the right approach and it will only be confusing later. Confused programmers make bad choices, and that usually leads to defects. If you're uncomfortable with a technique or feel that you don't understand it fully, don't use it. I don't use many exclamation points in these lessons, so you know I'm serious about this one. Not understanding a technique completely means you don't understand the possible requirements or side effects of using that technique. Maintenance coders may not yet have the skills to maintain code using advanced techniques. And if you're not 100% certain of yourself with the code, there's no way they will be. Comment your code. Certainly there's a right way and a wrong way to comment code. Proper code comments don't tell that something was done, they tell why something was done, and perhaps why at this location and not some other. Anyone reading the code will be able to tell that X was incremented by the width of the bounding rectangle, for example. But if it's not clear why, that needs to be commented as clearly and succinctly as possible. Remember, you're not writing that comment for other people. You're writing it for yourself a year or more in the future. Noting how to manage the lifetime of an object or memory block in a comment or two is a good idea. Help your future self now while you still have the opportunity. Finally, read everything you can find about how to write C++ code. Follow online discussions on Stack Overflow or LinkedIn or any place else that you can find where knowledgeable people offer their insights. If you've been a programming professional for a long time, see what's new with C++ 11 or C++ 14. You might be missing out on some new and powerful techniques that can make your professional life easier and more rewarding. If you're a new professional just out of college, remember that what you know now is just the beginning. The diploma says only that you've been educated to the point where you can actually learn. No matter whether you've been in the business 20 years or 20 minutes, the next lesson you need to learn is waiting on the road ahead.